Here's our sweet progress. It's pretty good. And here is our Pareto curve. This is pretty solid. There are a few things to figure out here. There are a ton of points grouped up over here. There's also too much encouragement to do this in the first place. Where's the first, solved point? At 20.9 over here. It's kind of crazy that it even found something this expensive. Let me say, what did it find? We're missing mini batch size, I think, here. Okay, so you can see here, it's intentionally pushed everything down to the bottom. Now this will be the graph that we want to see here. So okay, cool. I think this has mostly what we need. Mini batch. What's missing here? I think just mini batch. So here's the cost. Here's the front. So learning rate. I think we get the best results with the lowest learning rate. Just by a little bit, right? I would call this more of a stable region, I guess, but this, I think this is the best point right here. Is the one with the absolute lowest learning rate over here. This is an outlier, ignore this. Something happened with these points that we'll have to figure out. I think these are probably like the resamples or something. And then gamma. Yeah, anything from 0.9, what is this? 9.8 something? Yeah, 9, pretty much anything from like point. Really, it should be 0.99, it looks like, based on this. We might even want to increase this range. Lambda, a little bit more. Not really, actually, all the ones at the top are pretty high. 9.8, 9.9. Probably this one needs to be logit spaced. Update epochs, 1 gets you to 19. 2 to 20.5. 0.8. 9. Then the value coefficient here. Yeah, the normal 0.5 is fine. I don't know why it did all of this mess, but it does seem like anything over here is fine. It's cool. Maximum gradient norm. 0.5 seems to make it substantially worse over here, right? Gradient norm of 1, more stable. Entropy. Everything from virtually no entropy out to .01 is like, yeah. So pretty much there's good stuff anywhere in the entropy range for this env. Is this actually better? It looks like there are better points here. 20.9. Maybe. Number of envs. Okay, and batch size. Any of the batch sizes are good. This plot gets removed. Mini batch size. There we go. Up to 4096 it seems is good. There's degradation after 4096. I mean, this is kind of nutty. Pull restream up. We'll continue on this analysis. I mean, this is a good result. This is not a perfect result. The reason this is not a perfect result is made some very expensive runs. A simple env. I don't understand their filter thing. It just doesn't work. Well, that did it. Wait, no, it didn't. Why do I now only have... I have 99 items. Oh, there we go. It's funny, there is still a little gap here. All the best results are with a small number of envs. So there's a huge amount of different good learning rates. Learning rate's actually one of the most stable parameters for this end. Gamma is optimal at 995, which means I should extend that range. Probably on both of them. And 4 update epochs. Also, I have like 140 runs, and over 100 of them are 19.75 and up. And actually, they are almost all 20 and up. I still have 86 items. So still, learning rate in here is very stable, right? 0005. So this is 5e minus 4. One e minus 4. Looks like 2e minus 4 is a good starting point. And the original was way too high. Okay, this is definitely, now when you plot it this way, you can see you definitely have to expand gamma outward. Lambda actually doesn't matter so much. Right, lambda, they've done all these trials here, but actually the best ones are a little bit out this way. So gamma needs to go up a bit. I'm going to start on that, actually. No reason not to. So I forget if there's a reason I did this, but I doubt it. Do that. Gamma. To be fair, I did kind of fix the search ranges so it doesn't matter so much anymore. This definitely goes to 0.999 as a max. Then gamma, I'm going to leave it at 0.98 because I know Pong is, it's for other ends it can be different. 5, this is fine. Epochs, we're not going to let you do more than 4, it's ridiculous. Value coefficient. Yeah, looks like 0.75 or 0.8 is way better. The best result is at minimal entropy actually here. This is fine. Back prop horizon is reasonable. And yeah, at some point the number of m's just gets to be too bloody small. Batch size params look good. We're not going smaller than this for hardware reasons. Plus their points here. Okay. I'm going to try to look at the charts. That's actually, surprisingly, it's very stable. And actually, it's stable in not that many steps, isn't it? That's 10 million steps. With a bunch of high scores, right? It gets all the way back here. So it just pushed everything to the maximum time. It really didn't try very hard at the lower end of the Pareto frontier because there are all these stable curves. And like the shape is a little inconsistent at the start, right? Like maybe it takes you an extra few million steps depending on the seed. It was very stable overall. You see cost. Like, okay, it says that the best runs are at the highest cost, but there are only a few of them that are the best. And it's because it ran so many experiments, right? It says we have some as low as it's 130 cost. So a little over 2 minutes. And probably this point here could have been run for fewer steps. Okay. These are very good results then. The only thing we really have to think about is how this thing is budgeting its compute. Because the result itself is very good. No, we're happy with the sweep result. You can see there's still some diversity in here as well with the cost. So it's still doing different stuff. Let's take the filter off. Yeah, so you can see here in cost that there is a span here where it does a bunch of these very high cost runs that are probably pretty similar, but then it does spread out. So I imagine this is it filling in the frontier at the end. I mean, these early runs, like, so many of these runs, yeah. Interesting that it still misses a few of these, like hard misses. I guess it's trying to fill in lower end of Pareto front. I mean, this is the main chart, right? The Pareto chart. I have exactly the curve I want, but too much out at the high cost. And actually, I think I can scale 350. Yeah, I can just see how many of these things are above above like 300 cost. Okay, so we have 60 runs, so almost half of the runs, right? Between a third and a half of the runs are at the really, really high end cost. We need this to not happen. Okay, so there are a couple things going on here. I think the first is we're telling it that 29.9 is way, or 20.9 is way better than like 20.7. So we're overemphasizing the high end so much that it's scaling to max cost. we're also not penalizing higher cost at all. Okay, so the other thing that I haven't thought about here, I have this binary search aspect to my algorithm where it's supposed to fill in the gaps in the cost curve. But if you do that in linear space, right? If you sum up, if you just did like the cost is 1 to 10 and then you do that, you're going to get like 1 to 10. Well, the sum of 1 to 5 is 15. I believe 6 to 10 is 40, right? Because it's 55. So you're spending all the compute at the high end. One thing to look at here, there are good runs at the low end. Take a look at the algorithm. Pareto C norm. A 0, 1 norm. I see, so it is just the cost in a linear scale. If I do the cost in log distance, does that fix it? We can kill the palm sweep, I think. Because it's like, it's complete, right? I want to pollute the last point, so I'll let that finish. This is fine. Okay, so we have our sweep locked in. This is the first good sweep as well that we've gotten in a while, so it is encouraging to get such a good sweep as the first one with such heavy modification of the algorithm. And test this, and then we're going to test log cost. Oh, I'm kind of dumb, I guess, huh? Yeah, I'm kind of dumb here. This literally shows it to you, doesn't it? So this is what we got on the percentile task, right? And the top, this little chunk of data here is using half the compute. Okay, so this run, it looks like we did more data points, but this is the same thing, right? These curves are the same. Let me just check one thing with Visualize. Yeah, it goes to 1, not 0 here. This is fine. So, yeah, this is going to be an issue. Duh. Let me try the next thing. We'll do it in log space. Log C norm. I had to be careful to get that right. See if this evens the curve out. Funny. The most common question I get is probably about RL and trading. It's crazy. Important here. No. Really? I'm confused that that didn't do much. It didn't seem to do very much. No, it's slightly less, but it's not linear still. Okay. The next thing is going to be the score function. The next thing is going to be the score function, I think. So I don't know if I like this in log space either. Well, we will see. Let's go back. We'll do these one at a time here. The other one is the score function. I think I need to understand this score function. This is what you get for a score of 10. What you get for a score of 15, 18, 20, 8.5. Goes up to 6.9. Okay, so the epsilon factor is actually pretty nice. So if we do like -1 here, right? 20, this goes to 20.3 versus 20. This is almost linear, right? So I think that this epsilon factor is very important. This should essentially give you the aggression factor. I want to see what happens with 1e minus 1 first, to see if this is actually going to change the data the way I expect. The score transformation is very important. If you make it very aggressive, then the algorithm is going to bias very heavily towards trying to find runs that really, really max the score at any cost. But if you make it too passive, it won't find the best results. This is hilarious. Okay, so here is our, oops, this is before. Well, this is before, to be fair. The other one was with the different change. Okay, interesting. That also was not enough. Do I put them both together? Or both of these? And if this doesn't work, then we'll have to reconsider some stuff. Things won't make sense. To reconsider some scoring functions. Does the variability of the samples tell you much? Probably doesn't tell you a ton, right? Let me make sure that I actually hit visualize before. I did. So these two together fixes it. This is perfect. Yeah, this is a perfect curve. This is exactly what we want. Now the question is going to be, the epsilon term. Epsilon is the aggression factor, I think. Man, if this works, this way, this is gonna be awesome. This is gonna be so cool. Can you just publish? You just published a thing. Oh. Maybe. He's pinned. That's weird. I thought he had a paper, maybe not. So this is it, right? Yeah. Is it really this much caused by 1e minus 2 to 1e minus 3, that jump? Hang on. We'll rerun this again, and then we'll test 1e minus 1, 2, and 3. And then we'll test longer. Yo, Spencer. Yes, absolutely. I am going to do this morning session, get some breakfast, and then afternoon is perfectly good. And I can look at your code, we will chat about some research stuff, and I may as well even like go install the CPUs while we're chatting about that. Also, I think we have SOTA hyperparameter tuning. There are a few things I want to tweak, but I mean, I think we're going to have, and we have the result on Pong as well already. Where's the thing? Yeah, no, this is like really good. Yeah, this Pareto front here, this is perfect. Now, the only thing wrong with it is that I think it spends too much time on expensive runs. It needs to be, so it spends too much time on these expensive runs. It needs to spend more time over here. So we're going to figure out some configuration stuff with it, but I think we're just going to full solve everything with this. That's the hope. It's been quite a bit of work. It really has been quite a bit of work. I think there's still some left. All right, so this is the original that we had. Yeah, this is the original. You get this sort of a curve. Complex M's. We have a bunch of complex M's actually. I think that what we really need is we need more stuff on the research side. There's too many things I want to test, and I don't have people to do it. I mean, I think that you've demonstrated with the M's that you've built that you should be able to handle some of the research side stuff pretty well. We'll see. Maybe I'm overestimating, but I think in my mind the science is dramatically easier than the engineering. So maybe that's just because I've been doing it forever, but I don't think it's that hard. Okay, so the log cost has quite some impact. I think I need to run this for longer. Yeah, we need to get the original. Yeah, there's your original. Okay, we're gonna need to do 4 runs that are gonna take a few minutes, but whatever, you know. We really need to do it just to make absolutely certain that we have this correct. New run going on medium difficulty, steps per second back to 900K. That's what we like. That was very good. Ironically, so this hyperparameter stuff I'm doing, it doesn't like solve all the problems in RL, but I think that this gets our foot in the door. Like my hope is that what's going to happen is right now RL experimentation just feels very clunky and inconsistent. I think that if you have a really good sweep algorithm that you know that you can trust, um, then at the very least you're going to know, okay, I can run a sweep, and if it's just hyperparameters, it's going to find them. That's the goal. So then basically everything else that we do just becomes much faster because it's way higher confidence, right? You know how you just like everything is just slower when you don't really know for sure whether your experiments or whether the stuff you're doing is correct. So like you have to always second guess everything. I want to eliminate that from RL. So I took a quick look at that paper. It looks good. That's nice. They have 2 variations of 2 environments. So, yeah, ironically, the number of experiments that they ran would be like, we would do those in a few days on our few GPUs with like a puffer end. I think I've done more experiments than they have done for that paper, just testing this algorithm, just testing this hyperparameter sweep. It looks like very good work. I think Eugene's on it as well. Okay, this is the previous one. This will be the new baseline. Okay, these match, very nice, good. And then we gotta do log cost. Be the next one. Box 1 went down. I think I meant to go outside this morning to reboot it and I forgot. So let me finish this and then I will go reboot it and have breakfast and we will go from there. It's going to be much easier in the new facility where I just have to walk across the room to reboot stuff. So hopefully they won't be crashing. We're definitely going to do some good tests. Yeah, me on Discord whenever. I'm going to finish this morning session, another half hour, whatever I do here. And then I'm going to get breakfast and then I'll be around the whole rest of the day. See you, Spencer. All right. Two. That's already dramatically better. Still a whole bunch of points right at the end. The goal with this here, the goal with this change is to make this algorithm here. Maybe I should just, while this is running, I'll go through real quick. So this curve is the total amount of time spent in the experiments that cost up to this amount. So we spend a total of 15% or whatever of the time in experiments that cost 50 or less. So all these experiments cost very little. And then here you can see we spend another 20-ish% in experiments from here to here. And then you can see that the vast majority of the compute, 2/3, 3/4 of the compute, is spent on these experiments here. So the idea here is you're spending too much time on these expensive experiments. You'd like this to be more even. Oh yeah, this is the first one. This is our rerun of the same thing, so this is the same. And then this is with the modification. So now you can see that you're spending a little less than 2/3, it looks like, of the compute on these experiments. And then we'll see if this changes materially with the different epsilon. I think the main thing that you can see here is this sort of cluster of points, right? That you spend a lot of the compute right at the end here. There's this spike. And this is not just noise. The algorithm does this. To be fair, it does it way worse right here. So we've already improved this thing dramatically. The spike is gone. I think this is going to be the better one here. I think this is it. So the thing is that we could try, let me see something. This epsilon term is very important. It's not just like a noise term or whatever, so I should probably rename it. So this is, if we just do, actually, let me do 10, 15. Okay, so these points, this is with epsilon. Let's do actually 1, 2, 3. So you can see how this changes. So with epsilon of 1, 1e minus 1, we do 20.5. This changes by about, where is it? Yeah, from here, 28 to 5, 285, 3, 4-ish. So this gets about 0.5, 0.55-ish. Oh, and this still gains 1. Okay, this, I'm looking at the wrong one, my bad. Okay, let's look down here. So from 20 to 20.5, this goes up a little less than 0.2 and a little less than 0.2. So this thing is, no, I should just plot these, is what I should do. I should just plot these. That would be easier. This will be the quickest. Where's the green one? Okay. Okay, it doesn't actually seem to matter very much after, maybe it does. It's just hard to see. Oh no, it definitely does. Yeah, no, it definitely does. Yeah, let's get rid of this one though, because after that it goes crazy. Okay. This will be important. So right here, this is the reward graph. Put this where you can see it. So this goes negative. Is this pretty linear looking? That's pretty linear looking to me. It's just a shallow, yeah, line. So at negative 20 here, negative 0.3 or whatever, 0.16. Let me make sure I'm doing this right as well. Do I not norm? I thought I had a normalization operation on this. Yeah, this is screwed up. This should be above this, shouldn't it? Well, okay, let's say that this is 0 to 1 scaled. Okay. So the 0.1 is actually here. This is the one I think that we would want, right? This gives you eight. Okay, I didn't realize I just messed up the scaling. This is going to take a little more work. I'll be back in a few. Got to do a couple things, and then we'll take a hard look at the scaling, and we will finish the algorithm, hopefully. Be right back. Hello, Tyler, if you're still here. Sometimes X likes to eat messages. What are you graphing and why is it important? Okay, so this is the scoring function that we are using for the hyperparameter sweep. This transformation is applied to score data that comes in from the environment. And this is the transform I've come up with, and there are a few different, well, there's a parameter that can change the shape of it here. Okay, so interestingly, if we're going to say that we scale score data from 0 to 1, doesn't matter that it always be positive or anything like that. Doesn't matter. Should not matter. So I think the thing to look at here, how is it defined? By which policy? So the way that this works is you get a score from the environment after training, right? This could be your win rate. This could be like how many points you got in Pong or whatever. And we need some way to turn that data into a nice uniform space for the hyperparameter sweep to use. And typically, you want to accentuate the upper end of it. So like if you have a score from that's like a win rate, so like 0.99 is you win 99% of the time, and 0.9 is you win 90% of the time, you want there to be a big difference between those two. Usually this is going to work off of some sort of difference between scores. So you're going to look at the difference of the score of one run versus another, and you need the algorithm to actually care about the upper end of that range, but not too much. So there's a function that needs to be fit to that. So what I'm looking at here is essentially the slope at the upper end of the range. So for instance, here, if we go from 0.9, this goes from 0.25-ish to 0.3. So you only get 0.05. 3D. This is a 2D function. I don't think that this one would make sense to add more dimensions to this. Okay, this is good here. So this one you get hold on, you get, it's a little tricky. I need to take into account the whole range of this. So here's like your midpoint-ish, right? Loss. This isn't a loss, though. This is something that's fit to a hyperparameter sweep, not to an individual experiment. Yeah, loss space can be 3D, or I mean, loss space is very high dimensional. Okay, so if you set this one is I think 0.5, so I mean in the limit this is just going to become a line, right? So this is essentially linear. This one is 0.25. It's going to be something in here, I think, one of these two. So this one is virtually 0 to 1, a little off, but we'll call it 0 to 1. And we allocate it's like 0.75 and it doubles. So if this is 0.9, We might just have to test both of these. I think it's something between these two is going to be the best. I'm trying to think how environment dependent this would be as well. This is 5 squares, and then this is, what, 4 squares? This is reinforcement learning hyperparameter sweep, right? This stream is all about reinforcement learning dev. I mean, this is a sweep where every single point here is an experiment that achieves a certain score and costs a certain amount to run. I mean, and then we have data for a bunch of real experiments like this. And what we're trying to do at the end of the day is we're trying to come up with a method for running a ton of experiments and setting the hyperparameters of those experiments such that we are able to discover the optimal performance at any specific experimental cost. And ideally, we want to be able to find hyperparameters that make the environment train quickly and also perform well. And this is just one small part of the algorithm for that, though a very important part. I'm just trying to get a sense of how the scaling works here. If I just count squares, so 5 for 0.2, and then this is like 3, 2.5, and 2. A move 37 is, the problem with that is that it's dependent. You can't have a new, like, you can't really get that on an environment that isn't excessively played. That's really more of like a human thing than an AI thing. You need, that only can exist in an environment where people play it a ton and have like an established way where they're really confident that this is the way that you do it, and then they're just wrong. So AI can come up with awesome stuff all the time. We're just not going to know about it if we don't have a setting like that, if we're not using a setting like that. This one is the one that's, I think, the closest. The thing is, this is devoting, so this devotes half of the space to the last 20%. I think I'm fine with that. And then it devotes, how about to the last 10%? 30% of the space to the last 10%. 18% to the last 5%. Last 5% is 1 square. This is fine. And then a few percent to the last bit. So this is, I think that this one is probably the best one here. This is 0.1. The 0.01 is insane, I think. Yeah, this one is insane because this one here, if we try to get to 1, yeah, 1 at 2. Yeah, this one devotes half of its space to the last 10%. It could actually, that could actually be what we want. Let me think about that. So the margin of error is going to be to 40 is going to be like a percent, right? How much space does this devote to the 99% is my question. So 99 is right. 15% of the space is devoted to the last 1% of score. Okay. We have some options. This makes this at least makes some sense. Let's see if we can fix up the algorithm now with that. So the first thing is, I don't know why I didn't normalize the score coming in here. One minus one. Thanks for the offer, but no, I'm not going to accept that. Thank you, though. That's funny. That's cool. You do laser engraving stuff? That's very cool. Puffer doesn't get any swag until we once we cross 1 million in revenue, then we can get some swag maybe. But early stages, very, very early on. You know those startups that like they just like it's brand new, they don't even have anything, and then they've got like all sorts of t-shirts. I did I don't know, I took a course at Stanford. I did a little bit of laser engraving stuff. I mean it was just on wood. Yeah, it's fun. Back then it was just like an Adobe Illustrator file. I think that you could do, yeah, you could set the strength as well, so you could kind of etch. It was cool. That was fun work. I do sometimes miss like doing work in a shop. Being at the keyboard all day gets boring, even if you are working on cool stuff a lot of the time. But hey, we're making good algorithms here. Well, I have this set to 1 minus 2. Okay, then y norm. And you renorm like this. Norm. Rito YT. And then what score space do I change this in? GPYT norm. Yeah, this is fine. I think the rest of this is fine. We'll see if I have any bugs with this, but we will run this. We might now have to rescale some stuff. I don't know how I missed this before. I thought I'd normalized the input. I don't know if it'll make a huge difference here, but it could definitely make a big difference on Pong. This is pretty funny. Everybody's trying to sell deep research. It's like, yeah, okay, you give us a problem, we'll deeply research it for you. Now the question is going to be, did we completely break stuff? Either we completely broke stuff, or I'm just reporting... Oh, I'm reporting wrong. Let me see. What do we report? We report score, GPY, I mean, we'll see in a second, I guess. Yeah, we're not taking VC. We just bootstrap some stuff. Do contract work around RL. Okay, so this is very close. Almost identical, I think. So I don't think we broke anything massive. The predictions are definitely wrong here, so we probably just didn't report this correctly. This is GPY. Okay, so you take GPYT norm, you linearize, Oh, other way around. Norm. Should be this. GPYT. Norm. Then we'll try this with 1e minus 2, and we'll try this with 1e minus 1. Hopefully this should be substantially better. Yeah, the score and predicted are still completely different, so I still have something broken. GPY. Wait, hang on. Max score. Yeah, the inverse is wrong. Hold on. GP. Get rid of this. Visualize. I think that this should be like virtually identical, right? Yeah. There'll be a little bit of variation run to run, but this is pretty good. And now I think we fixed the score prediction. Did we use this for a GPY norm? No, because you use GPYT norm for the score. Okay. What are you doing? Fine-tuning this hyperparameter tuning algorithm. I'm tuning the hyperparameter tuning algorithm. We ran a bunch of experiments overnight. This is probably state of the art. This is very, very good, but there are a couple quirks with this tuning algorithm. The big one at the moment is, hold on. So there's just a ton of points right here. There's this huge just cluster of points all the way over here. So it should spread this data out a little bit more. And that will make the sweep substantially faster to run. Currently, the thing that needs to be fixed is, actually, I have a nice graph of it. There's a transformation that is applied to the scores that the environments get. And the one that I've come up with can be, it's kind of a family of transforms parameterized by this epsilon, which is this number here at the end. And depending on how you set it up, it either like really encourages you to push everything to the right hand side, to push everything to very high cost, or it doesn't encourage you at all. So we have to tune this parameter a little bit and just get a feel for how sensitive it is and stuff like that. The unfortunate thing with hyperparameter algorithms that have hyperparameters is who tunes the tuner. That's a funny little quip. Who tunes the tuner? Okay, this ran. Deep learning exam, and what course is this? My favorite ML class was Stanford's CS231N with Justin's lectures or Andre's lectures. Those are both good. Okay, it's in Germany. Yeah, cool. They have courses in this stuff now. Okay, so this looks pretty decent here. This is spot on with what we want. Yeah, this is pretty spot on with what we want. Let me make sure that this is... Oh yeah, no, this is perfect. And then the ratings here are pretty consistent. We need to be a little careful with the suggestions per Pareto, right? Can we OOM it? We shouldn't be able to OOM it, right? No, it should be able to handle a very large batch, actually. I kind of want to do this. I think it'll make it just a little bit more consistent. And then, well, that can't hurt it, so I think we'll be fine leaving that. Can it hurt it? It might actually be able to hurt it. Let me think. More samples technically means you have more chances to go off the rails, so we do have to rerun it for this. So we'll give it a second. And I think after this, we just test out one or two of the other synthetic problems, and then we run the Pong sweep again. We get cumulative cost. We'll tune. Yeah, good luck. All right, this looks fine. It's a little funny how it finds, oh no, because it's going to find higher rating stuff for a little bit. These aren't going to be consistent until it explores the whole front. So now it should start reducing, right? Yeah, so this rating term should decrease. And we'll be able to compute all sorts of metrics over that. You could even have this thing automatically terminated below a certain rating threshold, because this is just an estimate of how much value you expect to get from the experiment, right? That's pretty solid. So, I mean, we'll see. It's possible that this totally messes up the Pong sweep. But hopefully not. And I think we can just run this. You can see it's like, it's not expecting to get a ton from these runs now. It's just like, I mean, that's a very nice estimate. That's a really, really good metric to have. Holy. A hyperparameter algorithm that tells you how much value it has to keep running it. And actually, you could compute this metric. Ideas. I do have ideas. But that's a nice consistent metric. Oh, well, okay. If you're going to give me a perfect curve, I'll take that. Thank you very much. And look at that. Actually, this is good. It gives you in the elbow of the curve. Do you see how much coverage you have here? You'd want coverage here in the elbow. I'm going to run this on one more synthetic task, I think, and then I'm going to, I think we can just call it and run it on Pong. It's pretty solid as is. Pong mode. No CUDA GPUs are available. Really? Well, that's weird. Did my drivers crash somehow? Reboot the container. Random driver crash is weird. I'm gonna have to go get the token. And we shall see how this does. There we go. Okay. There are still a few things that we want to experiment with, but this should be enough to start running a bunch of experiments. I mean, a bunch of runs. Because I think anything else we're going to do with this, we'll probably want to run far more experiments. So we will let this go, and we will check back in a little bit to see how this goes. You see, we have a few folks on Twitch at the moment, so for anybody interested in following my work, this is live tons of RL dev. Puffer.ai, it's all free and open source. You can check it out right here. Start the repo to help us out. Join the Discord if you want to get involved. You can follow me on X for a lot more information on reinforcement learning and what we are doing. We also have a blog with lots of information, some of the latest developments in RL, but also quick start guides for beginners. So thank you, and I will probably be back later in the afternoon working on this some more.